Well, welcome back and welcome to the first of our videos for redox chemistry. So this is a unit that we said we would pick up at the end of this year, so let's get started. You should have come across redox reactions before, and probably more of them than what you think. Redox reactions are one of the largest class of reactions that we actually look at in chemistry. So let's just start off with what we want to try and achieve through this video and the key points that we're going to be looking at. What you should be able to do once you've watched this is explain the importance of redox reactions in everyday life, outline the different ways in which redox reactions have been defined historically and in the modern day, understand that oxidation and reduction occur simultaneously, and be able to identify redox reactions by looking at some example equations. So one of the reasons we look at redox reactions is because they are so prevalent in the world around us. If we think about the burning of fuels or any combustion reaction, really, they're redox reactions. So this includes the burning of petrol in cars, coal for electricity, the fuel we burn, the methane gas that we burn when we light a Bunsen burner. Any of those combustion reactions that give off energy are actually redox reactions. Corrosion of metals, so rusting, which is important to our engineering industry and society in general in terms of the strength of buildings, bridges, cars and everything like that, because we use so many metals. The understanding of how these corrode and what happens to them is something that's very important. Also, the opposite side of that is if we look at, we have refined metals that corrode. Well, we actually extract metals from ores, which is what this picture is here. It's actually a picture of bauxite, which is an aluminium ore. So most metals are not found in their pure metallic form in the Earth's crust. They are found as ores or compounds that have already reacted with oxygen and other compounds, and then we need to purify the metal out of that, and we do that again by redox reactions. Respiration, photosynthesis, so that process of breathing in, breathing out for us, so that gas exchange process is one of a redox reaction, but more importantly plants and how they go about creating glucose from CO2 and giving off oxygen. The respiration photosynthesis processes in biological systems are also redox reactions. Production of fertilizers, so superphosphate fertilizers and nitrogen fertilizers, they are produced by redox reactions as well, which means it gives us the ability to grow much greater amounts of crops than we would be able to without fertilizers, which allows us to support a much larger population, which could be considered good or bad depending on where you sit on that debate. But probably where you've come across them the most is the fact that all electronic devices, their batteries are powered by redox reactions, and we'll look at those in more detail later on in how we actually draw electricity from these reactions once we have a better understanding of what they are and how they work. But pretty much every battery, your car battery, your phone battery, the batteries in a Prius, everything that relies on a battery technology is relying on a redox reaction. So that's some of the reactions that are very important to us in terms of redox chemistry. Let's start having a look at them in more detail. So as we said in the startup, there are a number of ways that redox reactions can be defined. And we've seen in many situations in chemistry, as our understanding of the atomic model changed, our understanding of how we could explain things around us changed. So there was an understanding that things burnt, that there was a reaction going on, but for many years people couldn't understand what that was. There was a compound that was said to exist called phlogiston, which was meant to be the life force of something, and things that contained a large amount of phlogiston gave off that energy when they were burnt, leaving behind a phlogistonless compound afterwards, which of course sounds a bit crazy to us now, but this was before they'd even discovered oxygen. And then Lavoisier came along and discovered oxygen, and things changed. From then, our definition of redox simply became something that had reacted with oxygen, so it had gained oxygen, therefore undergone oxidation. And we can see that happening here with the hydrogen gas reacting to gain oxygen and form water. So this process in that case would have been considered oxidation. We can see this also when we have carbon or coal reacting with oxygen to form CO2, or sulfur to form SO2, or even in the rusting process where we have iron solid reacting with oxygen to form iron oxide. All these processes could be considered oxidation because they were having oxygen being added in with another element. That being said, as you probably have noticed, whenever we talk about oxidation, we also talk about reduction. So the opposite process was originally defined as a compound losing oxygen. So when oxygen is removed from a substance, that material has been reduced. Okay, so it was the opposite process of oxidation. And if we look at this, which is a hematite ore, the formula here, iron oxide, reacting with carbon monoxide gas to form iron solid and carbon dioxide gas, we can see that this carbon monoxide going to carbon dioxide would be considered oxidation because its amount of oxygen has increased. But the Fe2O3, well, the amount of oxygen has decreased, so that is called reduction. So that's one definition, by changing the amount of oxygen present in a substance. So here we see the reduction being the loss of oxygen, and oxidation being the gain of oxygen. So we can expand on that definition, which they did over time as they discovered more things, and realize that it wasn't always something that involved oxygen. Sometimes the same sorts of processes were going on where we could see a change in oxygen, but also hydrogen. So oxidation was said to occur when we increase the amount of oxygen, or when the amount of hydrogen in a compound decreased. So if we look at HCl in this reaction here between manganese oxide and hydrochloric acid, we see that we form Cl2 gas, which is the HCl losing hydrogen, so therefore it's been oxidized. It hasn't gained oxygen in this case, okay, but it's still said to be oxidized. Or another reaction that we've seen when we did organic chemistry is the idea of ethene. So our ethene reacting with hydrogen in a hydrogenation reaction to form ethane. Okay, so sorry about that. Ethane. So this is adding hydrogen in, so it's being considered reduced. When we increase the amount of hydrogen in a compound, we're said to being reduced. So if we increase the amount of oxygen, it's oxidized. If we increase the amount of hydrogen, it's reduced. Okay, and we can see that with a prac that we can do in a lab. If we take copper powder, so this is finely ground up copper, similar to what we extracted in the very first prac that we did way back at the beginning of our studies in chemistry. We put this into a tube with a gas inlet where air can come in, and we apply heat to the tube here. So it could be a Bunsen burner as our source of heat. The copper powder will heat up, the rate of reaction will increase, and it will react with oxygen that is present in the air. Okay, as it does that, it will slowly change color and turn black into copper oxide. Once we have that black copper oxide, our product, our copper, has been oxidized. Okay, it's reacted from copper powder, which is Cu solid, and it is now forming the CuO copper oxide. Okay, this solid here. So we've added in oxygen, so our copper has been oxidized. We can then reverse this reaction. We could now take hydrogen gas in, apply heat very carefully because hydrogen is very flammable, and steadily what will happen over time is that we will drive this back towards the copper. Okay, so we'll heat it up, we will reduce it, we have it in a reducing environment, and we'd be able to reduce it back to the original copper. So it's important here to realize that oxidation and reduction are two sides of the same coin. We don't get one without the other. So that's two definitions, our oxygen definition, our hydrogen definition, and then the one that we will more commonly see in modern chemistry is the idea that redox reactions are reactions that involve a transfer of electrons. So these reactions can occur even when oxygen isn't present. Okay, so we can have a redox reaction even if there isn't oxygen present, but in this case we're looking at the transfer of electrons. When we do this, we define oxidation as the loss of electrons. Okay, so if we think about our copper in going to copper oxide, when it does that, it goes from copper solid and it's forming a copper 2+ ion. So it's lost 2 electrons to form that ion. Similarly, reduction is the gain of electrons rather than the loss of oxygen. So if we look at oxygen gas, when it forms the oxygen 2- anion, okay, when it forms the anion, and we would form 2 of them, what's going to happen is one of these oxygens would gain 2 electrons and we would form O2-. So we can see that we have a gain or loss of electrons in each one. Again, oxidation and reduction can't occur in isolation. We don't see oxidation unless we see reduction going along with it. So there's a couple of ways for us to remember this electron transfer process, and that is that oxidation is where electrons are lost or produced, so they'll turn up on the right-hand side of any chemical equation when we have our half equations, and reduction is a process where electrons are gained, so we're going to see these on the left-hand side because they're going to turn up essentially like a reactant. They're being put in to the final product. So we can remember that by the mnemonic oil rig, where oxidation is loss of electrons, reduction is gain, or if you prefer, Leo the lion goes grr. So loss of electrons is oxidation, gain of electrons is reduction. I tend to use oil rig a lot, and I'll refer to this most of the time when we're talking about redox reactions. So these are the different ways that we can define oxidation and reduction: by electron transfer, by reaction with oxygen, and by following the hydrogen. Essentially, hopefully what you've realized now is when we look at electron transfer, essentially this means any time we form an ionic compound. We talked about ionic bonding early on in our studies, and we mentioned that ionic bonds form any time there is a transfer of electrons from the cation, from a neutral metal to a non-metal, forming a cation and an anion. So in this case with sodium chloride, when sodium donates its electron to chlorine to form chloride, we end up with this Na+Cl-. There's been a transfer of electrons. Sodium has lost its electron, therefore was oxidized. Okay, so in this case we have oxidation because it's lost electrons, and chlorine on the other hand has gained electrons, so it's undergone reduction. Okay, so in this case, anytime we see the formation of an ionic compound, we also have a redox reaction. So that's it for our definitions. So hopefully now, once you've gone through this, have a bit of a read of your textbook as well, and you should be able to explain the importance of redox reactions in everyday life, being able to give a few examples of these, outline the different ways in which redox reactions have been defined historically, their reaction with oxygen or hydrogen, or the transfer of electrons. Okay, understand that oxidation and reduction occur simultaneously, that we cannot have one without the other, and that now if you have a look at a few equations, you'll have a go at being able to work out if a reaction is a redox reaction by looking at whether or not something has increased in its amount of oxygen, increased its amount of hydrogen, or decreased its amount of hydrogen, or if we have that formation of an ionic compound, and we'll have a bit more practice with them. Okay, so I will see you in class.